Hello and welcome back to PC Retro Programmer. Today's video is on an advanced topic and we'll be programming the CGA card at the level of ports and registers, and for that reason the video is going to progress at a more rapid pace than a standard video on the channel, and I'll assume more background knowledge, in particular assembly language programming and some knowledge of CGA graphics. Now the question that I want to answer today is one that occurred to me when I was trying to understand more critically the function of the mode control register in the CGA card. The question is whether it's possible, even in a limited way, to get a high resolution 4-color graphics mode out of the CGA card. Now it turns out I already knew the answer to this, it just didn't occur to me, I hadn't connected all the dots. But the answer is strictly no, but interesting things happen when you try. At least that's the case on original hardware. So if you have an original IBM CGA card and a genuine CGA monitor, then what I say today should be valid. I don't recommend running this on later hardware like EGA or VGA. I'm not responsible if you screw your monitor up. Moreover, the conformance of video cards to the original CGA implementation of IBM varies. For example, I know that nothing that I say today is going to work on an Amstrad PC 1512 for certain, and it will or will not work on other clone cards depending on how well they followed what IBM actually did. It also probably won't work in any emulators at all. At least as far as I'm aware, there are no publicly released emulators that support all this correctly. Still, it's interesting to try these ideas out on various cards to see what actually does happen. So the question is basically to do with setting the card into a non-standard mode, what have been called improper modes. And for that reason I want to go through a little bit more detail what some of the bits in the registers do. So basically at port 3D8H you have the mode control register, which, as the name suggests, controls the video mode. It does a few other things as well. Then there's a color control register, which is for setting palettes and intensity, also background border colors, that sort of thing. Then there's a status register, which we can read to see when it's safe to access video memory without getting snow, and also whether we're in vertical retrace. And there's some light pen stuff, as I said, I won't touch on that at all today. So let's take a closer look at what some of the bits in the mode control register actually do. Now I should point out up front that I'm not the most qualified person in the world to talk about this topic. My source is the very good information on Reenigne's blog at reenigne.org. So you remember he is one of the authors of the 8088 MPH demo, which runs on the original IBM PC with CGA graphics card. So he and others spent a great deal of effort studying the card at the level of schematic diagrams, technical documentation, and one hell of a lot of personal experimentation just to see what works. So he's written up a lot of his own personal experiments on his blog, and you can check that out at a link in the description. So it's there that I heard about these improper modes. I'd stumbled upon a mode which made no sense at all to me, and he pointed out that he'd discovered these whilst poring over the CGA schematic diagrams, and that he'd written up a rudimentary description on his blog of what must be going on. So it's from that information and discussions with him that I was able to code these modes up and have some idea of what must be happening. So what I've done since then is try to really study these pixel by pixel to understand clearly the format and really clarify exactly what happens in practice. Unfortunately, these modes haven't proved very useful to anybody so far. I guess just the right effect for these modes hasn't been thought up yet, and so they're not described very much at all online, and even some of the information that is out there is not correct. So I really only have myself to blame today if I screw up, because it is something that I've tried to figure out for myself. but hopefully I'll describe it correctly because it's really not something you can just go and look up easily. In particular, I want to look at one of the modes today, which is behind the answer to my question about the 4-color high-resolution graphics. You can't quite get a mode that does that, but what you get instead is one of these improper modes. So let's discuss how these CGA ports actually work, and we'll begin with the bit 0 of the mode control register. And this is often described as switching between 40 and 80 column text mode, but unfortunately there's almost nothing about this description which is actually correct. First of all, from the point of view of the internals of the device, everything is characters, even in graphics mode. In fact, the CRT controller can't even count to 200 scan lines, which is what you have in the active portion of a graphics mode. And so you have to tell it that it has 100 characters in the vertical direction to display, each of which is 2 scan lines in height. And so it doesn't know or care where the pixel information for these characters is coming from. So in the case of what we call a text mode, it's pulling that information from some location in character ROM, and in the case of what we call a video mode, it pulls that pixel information for the characters from video RAM. So in fact, the first scanline of these 2 scanline high characters in graphics mode comes from the even bank of CGA memory, and the second scanline comes from the odd bank. So that's why you have this even odd bank situation. And the second thing about this is that the 40 and 80 column thing is just a convention. You can actually display more columns or fewer columns by fiddling around with the CRT controller registers. And so the 40 and 80 is really just a red herring. In fact, the character clock keeps running in all the border regions of the screen and so on, basically for the entire frame. And so you really need to know exactly how many characters wide the entire screen is to get this values here. And moreover, you don't just count characters, but you have to count scan lines of characters, because the screen has to be rendered in scan lines at a time, not characters at a time. And so in effect, what you'd have to do is multiply the total number of scan lines on the screen by the total width of the screen in characters, and then multiply by the frame rate. Now, you still won't get exactly these numbers here. There's a couple of complications. So first of all, the frame rate is not exactly 60 Hertz, it's actually 59.92. And if you multiply that by the total width of the screen in characters, which is actually 114 narrow characters in this case, and 57 wide characters in this case, and multiply that by the total number of scan lines, which is actually 262 on CGA, not 200 as you might imagine. That's just the active portion in the standard graphics modes, which can also be changed. Then what you end up with is these values here. So this is the number of scan lines of characters per second, whether it's displaying characters or not. So although this describes exactly what this bit does, it changes the frequency of the character clock, it's probably best thought of as switching between wide characters and narrow characters. Some people describe it as going from low resolution to high resolution, because obviously if you're putting out twice as many characters across the screen, then the resolution has doubled in the horizontal direction. So the next bit switches between what we'd call text mode and graphics mode. The text mode is obviously getting its pixel information from the character ROM, and the graphics mode is getting its pixel information from the video RAM. Also in the graphics mode, the snow suppression circuitry gets switched on. You won't get snow in the 40 column text mode, but in the 80 column text mode, at least on original IBM hardware, you'll get snow if you try to access video RAM at the same time that it's accessing it to try and figure out which character to display. So in later clones, this didn't happen. It varies between card to card. but there are cards that don't have snow even in the 80 column text mode. Then you have the color burst bit. Now this is for composite output. If you enable this, then it'll go to monochrome on the composite output. But it also has the effect of setting the color 2 in the 4-color palette to red if it wasn't already red. So in palette 0, that color is already red, so it has no effect. But in palette 1, it is magenta normally, and so this actually gives you a third palette, which is undocumented by IBM. The next bit is self-explanatory. It disables or enables video output. So basically, when it's disabled, it just blacks the screen as though zeros were being presented for the pixel information. And then bit 4 switches between 2 bits per pixel and 1 bit per pixel. So this is just how the pixel information is interpreted in terms of colors. So in the 2 bits per pixel mode, you obviously have 4 colors, and in the 1 bit per pixel, you just have 2 colors. So it's really 3 colors plus background in this case. So the background color can be set here in these bits of the color control register. It also controls the border color in that case. In the 1 bit per pixel mode, you have just a foreground color and black. And so the foreground color is set here. And this 4 bits here, by the way, also sets the border color in text modes. So it has 3 different functions depending on what mode you're in. Bit 5 here enables or disables blink bits. So in the character information in video RAM, one of the bits can be used to blink the character if this is enabled. Otherwise it just stands for the normal intensity bit. So now we come to the color control register, and I've already explained what these do. It's either border plus background color, just border color, or the foreground color depending on which mode you're in. And then you have the low intensity and high intensity palette. So the 2 bit per pixel palettes, there are 2 intensities of each of the palettes. And here is the bit that sets the different possible palettes. So there are just 2 palettes. There's the ugly green, red and yellow, or it'll be brown in low intensity. And there's the ugly cyan, magenta and white, which would actually be grey in low intensity. And so as I said, this bit 2 up here will change this magenta to a red if it's enabled. So then you have a status register which you can read to get some information. So bit 0 tells you whether you're going to get snow if you try to access the video memory in the 80 column text mode. And if it's a 1, then you can definitely access the memory without snow. The bit 3 also tells us whether we're in vertical retrace or not. So that's how we detect the vertical retrace time. And finally, there's some light pen stuff which I won't touch on in this video. So I think it's time that we just code up this improper mode and see what happens. But before we do, we better set up our screen geometry so that we don't have the monitor losing sync. So we'll have to set some values in the CRT controller, the 6845 chip or equivalent on your CGA card. And you can see that it has a whole bunch of registers that we can set. And we do that by sending the register number to port 3D4H and then send the value for that register to port 3D5H. So I've put in all of the default values as I understand them for the 40 column, 80 column text modes and the graphics mode. So the first block are for the horizontal setup, so the total number of characters horizontally across the screen. Actually there's one more for the border, but you don't count that when you set these figures. And the total number of displayed characters, of course that's going to be 40 and 80 in the text modes. And in the graphics modes, it turns out to be 40 as well. So for example, the 2 bit per pixel graphics mode, there's going to be 4 pixels per byte, and there's 2 bytes per character. So that gives you a total resolution of 320 in the horizontal direction. So then there's the horizontal sync position. It's a little bit higher than the displayed characters but lower than the total. So we put the sync at the right place so that the screen looks centered basically, and the sync width is usually set to 10. You can shrink that a little, but it's best to leave it alone. Then in the vertical direction you have the same thing again, so there's a total number in the vertical direction, and again you add 1 to these values if you want to include the border, but this is not what you do when you set the values. Then there's the number displayed, and as I said previously, in the graphics modes you have a resolution of 200 in the vertical direction in the active area, and this is actually 100 characters of 2 scan lines height. Then there's the vertical sync, of course, that's again between those 2 values. This won't quite give you the full 262 scan lines if you do this. Obviously if I take 127 and add 1 I get 128, and there are 2 scan lines per character, so that's 256. So I'm actually 6 short, and so you have to adjust it with 6 additional scan lines, and that's what this register's for. This is a mode register. This is just always set to 2. The IBM BIOS just doesn't use this at all. It does things like interlace and so on, but it's just not set up to use this. There's the maximum character scan line. So in graphics modes, this will be 1. You'll have scan lines 0 and 1. So 1 will be the maximum one. Of course, in the text modes, the maximum scan line for the characters is 7. So you'll have 0 through 7 because the characters are 8 scan lines high. There's the scan lines for the cursor within the character if you have the cursor displayed. And this is the start address where it starts reading from video RAM, where it starts reading data from video RAM, and that's just usually set to 0. We'll fiddle with that in another video, and I'm not going to bother with any of the rest of it here. So those are the values that are default, but of course our mode's a little bit special. I suspect what we're going to end up with is the higher values in the horizontal direction. So we'll basically have the values from the 80 column text mode in our graphics mode, and the vertical stuff will be the same as for a graphics mode. So what I'm going to do, I'm going to assume that we're starting in the 80 column text mode, so we won't need to change these, but we will need to change all of the vertical values. So these 4 will get changed. In fact, this one won't need changing because you can see it's 6 for all 3 modes. So I'm going to have to change 3 of these values with some code. So let's take a look at how I've actually done that. So I've written a small program here called highres.asm, and this is where we set all the values and just put some data in video memory. The code is quite straightforward. The first thing that we do is switch into the improper mode that we're interested in, and I'm using Reenigne's notation here in my comments, plus hres plus graph minus 1 bpp. So this means that bit 0 will be a 1, which means the narrow character or high resolution mode. Bit 1 will be a 1, which means graphics mode, and of course we need bit 3 equal to 1 because we need video enabled. But we don't want 1 bit per pixel, hence minus 1 bpp. We want 2 bits per pixel, so that's a 0 in bit 4. And so all of that goes out to port 3D8H, the mode control register of the CGA card. So that sets the mode, and now we need to set up our screen geometry. So I'll have to set some CRTC registers, and the first one is register 4, which is the vertical total. And I just set this to the maximum possible, which is 127. So we use our standard trick of outputting to ports 3D4H and 3D5H with a single instruction, out dx AX, and we do that by setting the value for 3D4H in the AL register and the value for 3D5H in the AH register. So Register 4 and value 127. That's what this little computation is about, which the assembler takes care of for us, of course. So then I set the vertical displayed to 50, so 50 characters, and we're going to have 2 scan lines per character. You'll see a little bit further down. And so the reason that I've done 50 instead of 100, which is what you'd normally do in graphics mode, is because we don't have enough video RAM for 100 characters in the vertical direction. At 2 scan lines each, that'd be 200 scan lines, and because each scan line takes 160 bytes, that's almost twice the video RAM that we actually have. So I have to use 50 characters instead, so register 6 has the value of 50. Now I could have used a vertical sync of 112, which would be the standard for graphics mode, but I want it to be centered more in the vertical direction. So if I fire the vertical sync pulse earlier, that has the effect of moving the screen down, and so register 7 is set to 87 here. Now here's where we set 2 scan lines per character. There'll be scan lines 0 and 1, of course. Remember, all the even scan lines are going to come from the first half of video memory, and all the odd scan lines will come from the second half of video memory. So the maximum scan line is 1, is 0 and 1, and so we set register 9 to 1. And so now we're on to just filling up the video memory with something to look at. So I'm going to start with color 0, so it'll just be black. And we'll fill the first 25 scan lines of the even bank with that color. So each scan line is 160 bytes. And then I'll switch to color 1. So I want 1 for each pixel in the byte, and that just works out to a value of 85. And so it loops around for a second go and does the next 25 scan lines in color 1. Now I've only used up 8,000 bytes of the even bank at this point. There's 192 bytes remaining, and I don't want garbage in there, so I just zero those out. Then I switch to color 2, so each pixel in the byte will have color 2, which is value 170. And we do the same thing again, basically. 25 scan lines in color 2, add 85 to the color, that'll take us up to color 3, and another 25 scan lines when we loop around for the second iteration. And finally we have another 192 bytes of video RAM that needs to be zeroed out, just so there's no rubbish in there. And we wait for a key press, restore the video mode, and exit to DOS. So that's all there is to it. So now let's save this and assemble it, and I'll run it on some genuine hardware, and we'll see what actually happens. Well, this is how everything looks on a genuine IBM CGA card, and I'm using palette 0 here, which you can set at port 3D9H, of course. And this is red, green and yellow with the background color. And apart from this weird black line down the left hand side, everything looks more or less as it should. We have black lines interleaved with red lines and green lines interleaved with yellow lines, and that's what we'd expect. And apart from the fact that it's only filling half of the screen because we don't have enough video RAM for a high resolution mode with 200 scan lines, this is exactly what we might hope for if we were to have a high resolution 4-color mode. But unfortunately, not everything is as it seems. So what I'm going to do next is write a little program to jump through the bytes in video RAM and successively set them to 0 to black them out. And we'll see what happens when we do that. Well, this is what I have now. First of all, I'm using palette 0, as I already mentioned. So it's just a matter of sending 0 to port 3D9H, the color control register. This will also set the background color to 0, of course. And then the next change that I made was to start at color 1 instead of color 0 when I'm filling video memory. This will just mean that there's a color in every line, and so we'll be able to see the black when I blank out bytes by setting them to 0. So then the next thing that I do is when I filled video memory, I wait for a key press, and then I save the first byte of video memory into the BL register so I can restore it later, and then I put 0 in instead. So that'll blank out the first byte of video memory once I press the first key. And then I have a little cursor loop. I really couldn't be bothered screwing around with scan codes, so I didn't actually use cursors in the end. So what it does is it waits for a key press, just using our ordinary int 16H. But this actually tells you what key was pressed. So if you look in the AH register after it runs, it'll have the scan code, and if you look in the AL register, it'll have the ASCII code. And it's a little bit easier to work with ASCII codes if you can, so I'm just going to use letter keys so I can identify them easily. And so the first thing it does is check if the Q key was pressed, and if it was, that has ASCII code 113, then it jumps to the end of the program and quits. If not, then it'll check for a D, which is ASCII code 100, and if not, it'll jump down to the next check. But if it was a D, then what it's going to do is restore the byte that we saved earlier, so in other words, restore the one that we already blacked out, move to the next video location, the next memory location by incrementing DI, and then save that byte into BL, and then blank that one out in video memory. So that'll basically just move our little black blob to the right on the screen, hopefully, if everything's working correctly. And then after it does that, it'll just go back to the beginning of the cursor loop. Now, if it wasn't a D key and it jumps down to here, it'll check whether it was an S key, and this has ASCII code 115, and if that's not correct, then it'll just jump back to the beginning of the cursor loop and wait for another key to be pressed. So if it's an S key, then it does exactly the same thing as it did above, except we're now going to move down one scan line. So of course we have to worry about the even odd scan line thing, and so this is the usual piece of code for moving down one scan line. And then as usual it saves the byte on that scan line and then sets it to 0 in video memory and goes back to the start of the cursor loop. So it's really just a very straightforward way of allowing us to press D to move right on the screen and S to move down on the screen. And here's the end of the program, which is just normal. Once you press the Q key, it'll jump down to here, restore the video mode and exit to DOS. So let's run this on our original IBM CGA card and see what happens. Well, this is what it looks like now, and of course if I press a key it'll blank the first byte of video memory, and if I press D it'll move to the right by 1, and that's black anyway. The next one is black, that's good, and now unfortunately it blacks 2 bytes instead of 1, so something doesn't seem quite right there, unfortunately. And if I keep moving across, the pattern repeats: 1, nothing, 1, 2, 1, nothing, 1, 2. So what's on Reenigne's website is basically correct. Some of the bytes are repeated, and apparently this is due to the snow suppression latching the addresses at the wrong time. And if I move down in video memory, exactly the same pattern repeats over and over. Unfortunately, it's the same on every line. So yeah, this is not really a very usable mode, unfortunately. So there's really nothing we can do about this on original IBM CGA. So what I'm going to do is try some of my other CGA cards. I have another IBM one with a green PCB instead of a brown one, and I also have another couple that I'm going to try out and see whether there's any difference, for example, on the clone cards, and then we'll run it on an Amstrad PC1512 just to see what happens there. Well, this is the other IBM CGA card, and the behavior is basically identical. You see it goes 1, 2, 1, 0, 1, 2, 1, 0, and the only thing that I've noticed is that when I start it up, sometimes it shows without the black line down the side. This is what that looks like, and you can see the behavior is the same. It just doesn't have the black line down the side, and the picture I think is slightly shifted to the right. I'm sure the other card starts up in this mode equally often. They're almost exactly the same card. Now this is my Multitech card with model MPF-PC. It's got some weird model number PB8307020-2B. And this card always seems to start up in this mode, which is rather interesting. So no black line, and the behaviour unfortunately is exactly the same as the IBM cards 1210, etc. So now I'm going to try my Amstrad PC1512, and I have one other CGA card after that. This is the PC1512, and as you can see the picture now fills the full screen, but there are actually 50 scan lines here that are green, so this is not a high resolution mode, it's just using low resolution mode, and so we end up with twice as many scan lines because we've filled that much VRAM. So that's a bit of a shame, and of course everything works perfectly in terms of moving about. So this is exactly what you'd expect from a normal 4-color 320-200 display mode. This is my other CGA card. It's also a Multitech CGA-PC with model number PB85048-3A. Seems to be a later card. It doesn't have snow in the 80-column text mode, so we might expect this one to behave a little bit differently to the other cards. So let's start it off and start moving across, and voila, look at that. So yeah, this one actually has every byte correct. Let's just move down scan lines. Yeah, everything seems to be fine on this card, so we actually have a high-res 4-color mode on this. Naturally, that's quite exciting, so what we should do is some color mixing. The pixels are so fine in the horizontal direction that we shouldn't be able to see them individually, which means that if we alternate colors, we should get mixed colors essentially. So we should end up with the effect of more than the 4 colors in the CGA palette. Well, I looked up the RAM that's used on these Multitech cards to try and figure out why the second card is so much better, especially in the 80-column text mode and also in this improper mode. So it was my guess that either the RAM itself doesn't suffer from the snow problem at all, in which case there's no point having any snow suppression circuitry, and so it's not interfering in this improper mode, or it could just be that the second card has much better snow suppression circuitry, which happens to work in the 80-column text mode, and as a side effect works in the improper mode. So I don't know the answer to that. I do know that the first card uses dynamic RAM, which is much more difficult to interface with. You usually need a clock, and you access the addresses in memory by row and column, and you need a periodic refresh so it doesn't lose its contents. It's just all round more difficult to deal with. The static RAM in the second card, of course, is much more expensive. It was used in caches and things like that. It's usually much faster, and you just basically enable the chip and select the mode you want, read, write or whatever, and send it the address, and out comes the data. So it's really very easy to use in comparison with dynamic RAM. But from the data sheet alone, there's not enough information there for me to be able to understand whether or not this particular kind of RAM could suffer from this kind of snow problems that we see on the other card. So I still haven't got an answer to that question, and I'd really have to trace out the PCB on the CGA cards to see what the differences are, and that's just a project for another day. So let's take a look at the code that I wrote to really confirm that we have a high resolution mode. As I said, if we do, we should be able to mix the original CGA colors to get new color combinations. The pixels should be so small in the horizontal direction that we shouldn't be able to see them individually. So if we alternate the original CGA colors, we should get new combinations. And the way I'm going to do it is to put 16 stripes on the screen, and we'll just go through all the color pairs from 0, 0 up to 3, 3. There's 16 different possibilities, and each stripe will be 10 bytes of video RAM wide, So there'll be vertical stripes, and of course each scan line is 160 bytes, so that gives us 16 stripes as we want. And so basically the program starts the same way as it did before, just setting up the video mode, and we start with color combination 0, 0. So I'm going to do 50 scan lines in the even bank first, and this will obviously write 10 bytes in the current color and then just increment to the next color, and it'll just keep doing that until it has finished all of the different color combinations. So obviously 2 pixels for a color combination is only 4 bits. So when we increment AL, we have to AND with 15 to get the lowest 4 bits, but then we need to duplicate that in the upper half of AL, so we get the same color pair in the upper half as the lower half. And so there's this little piece of code here for that. So just make a copy of those 4 bits, shift them to the left 4 bits so they're in the top half of AH, and then add it back into AL. So now we have the same color combination in the bottom and top half, and then I check whether we're back to color combination 0, 0 again. If we are, then we've done an entire scan line. If not, then we just keep going until we finish the scan line. And then I do 50 scan lines, and the scan line counter is in BX, obviously. So now we have a total of 8,000 bytes of video RAM filled up. Of course there's 192 bytes of the even bank left, and I just don't want rubbish in those, so I zero that out. And now we have to do the odd bank, and I want exactly the same thing in the odd bank. So we have another 50 scan lines of the odd bank. But rather than duplicate the code, I'll just keep track of whether I've got to the end of video RAM yet. If DI is 16384, we must be done. If not, then I just do the whole thing all over again. So that fills video RAM, and now the idea is to iterate through all the different possibilities of background color, intensity and palette, just so we can see all the different combinations that are possible. So there's 16 different background colors, 2 intensities of palettes and 2 CGA palettes, and that makes 64 different possible values in the O3D9H color control register. So I just iterate through all of those and just wait for a key press each time. So that's all that code is doing. Now we haven't touched the undocumented palette at this point. Remember that only works with palette 1 of the CGA, or at least it only makes a difference in that case. So we need bit 5 of 3D9H to be a 1 in that case. So there are actually only 32 possibilities for the undocumented palette. And so this loop here takes care of all of those. So now we're done, basically. It quits, and so we should be able to just press a key and go through all the different possible palettes, intensities and background colors with our 16 stripes in video RAM and see what it all looks like. And if we see 10 different colors for many of these palettes, then we should be in a high resolution mode. So let's check it out and see what actually happens. Well, this is looking very promising. Definitely more than 4 colors there. So let's start scrolling through and see what happens. Oh wow, that is really impressive. I'm not sure how well this shows up on camera, but that just looks fantastic. Let's scroll through some more here and see what they look like. Yeah, these are great. Oh, wow. So there's definitely 10 colors there, and I can't see the individual pixels for sure. I guess there should be a total of 64 plus 32 palette combinations here, which I guess makes 96 in total. Plenty to choose from. I guess we have a lot of fun that we can have with this. I'm so pleased this works.